Hello, everyone, and welcome to this lecture on modern analytical chemistry and specifically, I guess, instrumental analytical chemistry. Last time we talked a lot about waves, we talked about absorption measurements, we talked about emission measurements. Now we're going to get into a little bit more about the inner workings of some of our instruments so that we will have a better understanding of just what processes are going on inside, and if ever there are any issues, we will be able to give a meaningful input on how to solve those problems. So typically, whenever we're using optical instruments of the kind that we'll be using, like most commonly we'd be finding in an analytical chemistry laboratory in a workplace, kind of instruments like UV vis spectrometers, HPLCs, GCMSs, many of which atomic absorption spectrometers, many of which make use of the absorption of light to actually measure our sample. But there are others which are involved with things like fluorescence, phosphorescence, scattering, emission, and chemiluminescence. Scattering is especially important with regards to things like colloidal suspensions, things like milks or suspensions of nanoparticles. They're very good at sort of maintaining quality control and ensuring quality assurance at all times. So in all cases here, the response is going to be proportional to the concentration of the analyte. So there's going to be some sort of calibration curve which we can create. If we recall back before, we saw that in our calibration curve, we had different sensitivities if we had different gradients. So as our gradient changes, our instrument became more sensitive. And as the difference between the gradients of, say, two different analytes changed, so as long as their gradients were significantly different, we could suggest that the instrument was more sensitive to one analyte over the other. So this is the idea that response is equal to proportion, or the proportionality constant times the concentration. Proportionality constant just really comes from that gradient of the calibration curve, and that's mainly how we can obtain it. So in general, our optical instruments, which are making use of any one of the phenomena on the previous slide, they're going to have a fairly similar structure. So the first thing is we have to have some light source. So that's where we're saying here we have this radiation source. That's going to be our light source. So like, I mean, if we're going to be measuring absorption of light, the light has to come from somewhere. Unfortunately, the light from just like the sun or whatever is not really intense enough or of a correct wavelength to be utilized in most optical instruments. It is sort of the basis of how people came up with the idea to do this, but modern instruments do not use the sun. Some sort of transparent sample holder. Now, this doesn't need to be transparent to the human eye. It just needs to be transparent to the radiation which is passing through it. So, for example, in cases of infrared samples, you don't necessarily need to have a sample holder which is transparent to us. So long as it's transparent to the infrared radiation, then it's okay. Some sort of wavelength selector. So this is important because we want to be able to record our phenomena, the absorption, the emission, or whatever, at specific wavelengths, so that we can attribute the absorbance at a wavelength to its intensity. So that means eventually we can say, like, you know, this is the best wavelength to measure this particular analyte. Then we want some sort of radiation detector, which will be our way of converting our radiation that is either remaining after the absorption or has been emitted, and converting that into an electrical signal, which is then passed through an electrical circuit to our signal processor, and then the signal processor will change the electrical signal into a number, and that number will be read out on a screen or on a piece of paper, or in some way it will be provided to us as a written sort of or readable, source. So here's the schematic. We saw this before whenever we were looking through waves of a typical absorption spectrometer setup. So we have, as I said before, this tungsten lamp, which is our radiation source. Then this light will, as a light bulb often does, it gives out light in all directions. So we need to use some sort of collimating lens. So what that is just a fancy word to say that it's taking this diffuse light and parallelizing it so that all of the beams of light are parallel to each other. So a lot of light will be lost in other directions, but that's okay so long as the light that we do get will be put into parallel lines or parallel waves. There would typically be some sort of box around the tungsten lamp to absorb any extra excess light that's not being used, and only the light which comes out of that box goes through this lens. Then after the beams of light, the waves have been properly collimated, they pass through a filter to remove any unwanted wavelengths, and then a shutter, which is used to just turn the light on and off. And then this variable diaphragm is an optical instrument which will set our transmission to 100%, although this is not really, strictly speaking, always necessary. You can use this to say, for example, our light intensity is too strong and the filter hasn't reduced it by enough. We can use this diaphragm to reduce it some more. Then this light will pass through our sample next. So in this case, it's not capable of measuring both the blank and the sample simultaneously. So it measures one and then the other. So you would have some sort of shutter or shunter to move these between the different positions. Then the light passes through here, and then we get to the photoelectric device. The photoelectric device has some interaction with whatever light is remaining. It can be, if we recall back the different energy states, it can be because of an increase in electronic energy state, or the idea that it absorbs some amount of this radiation. That radiation creates a kind of excitation within the material, the photoelectric device material. And then whenever that relaxes again, it causes the movement of electrons through the device, which is then can be passed along an electrical current or electrical circuit. And then that can eventually come to the signal processor, which can be a digital meter, could be an I/O board of a computer. Typically, it's now an I/O board on a computer, an input-output board. But it can also be a digital meter. Actually, in some ways, a digital meter is probably better. It's more future-proof, although it gives us less detail about the measurement. So photoelectric device is a transducer that converts non-electrical signal to electrical signal. We saw that before. So that's an important thing to realize, is that whenever we're measuring these things, we're always just measuring the electrical signal that's produced from a non-electrical signal. So here are some of the wavelength radiation sources. So it depends on what spectral region we actually want. So we have here like UV, we have visible, we have near IR, IR, far IR, and we can have two different types of sources. We can have continuum sources and we can have line sources. So what are continuum sources and what are line sources? Well, continuum sources are continuous. They produce light over a broad range of wavelengths. Now, as we'll see in a little while, different wavelengths do not necessarily always have the same intensity from a particular light source. Typically, these light sources have a peak in their emitted light at a certain point. That usually corresponds to that 1:0 relaxation within the material itself. And then line sources, they produce very, very small, narrow wavelength ranges, which makes them very specific and very useful for measuring very specific types of materials, or knowing exactly what wavelength you are exciting or using in your measurement. So here, for example, we have a xenon lamp. So typically xenon lamps are used in conjunction or sorry, not xenon. Hydrogen lamps and tungsten lamps are typically used in conjunction with each other in UV visible spectrometers, because the hydrogen or deuterium lamps are active over the full range of the UV when used in conjunction with the tungsten lamp, which can also cover the visible range. And both of you could use a xenon lamp, but the problem with xenon lamps is they're expensive. So typically it's a combination of these two, which are both relatively cheap. LEDs can also be used. The problem with most of these ones is that they don't cover the full range of the UV, and so cannot really be used in the UV vis spectrometer alone. The xenon lamp could, but as I said, it's expensive. It's expensive to replace because these are light bulbs. If you're familiar with light bulbs, eventually they do stop working, the filament breaks or something goes wrong, and then they have to be replaced. So usually most people opt for the option, even though it's two different types of bulbs, it's still cheaper than a single xenon lamp. Then the Nernst glower, the nichrome wire, so this is just a wire which produces light, and the glow bar. We'll learn some about some of these, but for the most part, it's just to understand that there are radiation sources which can cover the entirety of the electromagnetic spectrum, and that there are two different types, continuum sources and line sources. The line sources produce very narrow ranges of light, and the continuum sources create very broad spectrum of emitted light. Then detectors as well. So this is important because we'll have different types. We'll have photon detectors and thermal detectors. Photon detectors, as the name suggests, will detect the electromagnetic radiation. How they detect it varies, but generally they're based on this idea of absorption of the emitted or the entering light, and then that entering light will be kind of utilized to form an excitation, and then that excitation will release an electron, and that electron can be utilized to create some sort of meaningful and measurable electronic current. So photographic plates, photomultiplier tubes, photocells, silicon diodes, charge transfer detectors, photoconductors. These are all things that we'll talk about as we go through. Generally, what they do is they take an electron and they utilize it in an electrical circuit in some way. But we will learn about how each one of them does it briefly. We won't go into a huge amount of detail except in a couple of cases. And then thermal detectors, these are measuring sort of the heat which is produced from our measurement, instead of necessarily the light. They're trying to detect the thermal energy which is emitted. So that means that they're very good at covering the infrared regions of the spectrum. So continuum sources produce broad range of wavelengths. They're often black body sources. Heated solids such as glow bar or nichrome wire, they can produce in the regions of 1 to 40 micrometer wavelengths. Tungsten lamps, as I've said, are usually the ones we use the most. So they have a broad range as well, 300 to 3000 nanometers. So they can often be used in a diverse range of applications. Typically, though, they see most use in, as we saw in the range back here, in the UV vis and near IR. They don't really see much use in IR. Typically, what's used in IR is like a nichrome wire. So then quartz, tungsten, halogen. So this is a combination lamp, which tries to modify the tungsten lamp in such a way that it can introduce a lower wavelength radiation. So it can go from 200 to 300, which would cover the UV range as well as the visible range. So it sort of operates at a very high temperature there, 3,500 Kelvin. It's very hot. I mean, whenever you consider that we are at about 300 Kelvin, this is more than 10 times hotter than that. So it usually needs to have some cooling. It needs to be handled very carefully with its heating and cooling, because the thermal expansion involved with the glass and stuff at that kind of temperature, and when we shut it off, means that it's very prone to shattering or cracking. And these things are not cheap, so it usually there's a very specific turn off procedure involved with all of these things. You can't just flick the switch, turn it off, because if you turn it completely off, you might also turn off the cooling to the lamp, at which point you probably destroy the lamp. If you do it well, usually the first time you can get away with it, but if you do it more than once, usually it ends up breaking it. And then so what the process that's happening here is this high temperature is causing the evaporation of the tungsten metal off of a filament into the to the gas inside of the lamp. And then this gaseous tungsten this process here is what is producing the light. Then inside of the sheath of the lamp, there is iodine gas. So the evaporated tungsten, this W means tungsten. Tungsten will react with this gas to provide tungsten iodide. And this reaction actually improves the lifespan of these lamps, because it helps in the redeposition of the tungsten. See, if it, I know it seems a bit strange, but like the tungsten as a gas may or may not redeposit back onto the tungsten solid in the way that we wanted it before. Whereas actually reacting it with the iodine first and then having it be redeposited actually improves the lifespan, improves this redeposition property. So what we have here is the tungsten iodide depositing back onto the tungsten to give us just the tungsten regenerated plus the iodine gas regenerated as well. So it's kind of like a nice little loop wherein the iodine is used to help redeposit the metal. It's also regenerated at the end so that any further tungsten which is evaporated can be redeposited again. So this is where I was talking about before, this idea that different light sources do not necessarily produce continuum high intensity radiation. So here we have a deuterium hydrogen lamp. It produces continuum UV light. This is the spectrum of, I think, deuterium. And then what you can see here is the intensity of the light here versus the wavelength. Now, you can see that there's a very clear peak here at around about 240 nanometers, and then that drops off. So what that means is that the amount of light that's being provided at 300 nanometers is going to be less intense than the light produced at 240 nanometers. And so this can have consequences for our sample, because if our sample, for example, cannot absorb the 240 nanometer light, but it can absorb the 300 nanometer light, but then this intensity is not sufficient, then it won't really absorb in the way that we had hoped. So usually there are kind of like inbuilt mechanisms within the instrument. Well, at least sophisticated instruments, modern instruments usually have some sort of like moderator for the power inside of the emitted radiation intensity inside of the instrument. But older ones or simpler ones or lower cost instruments typically don't, which means that you have to be aware of this issue if you're not getting the absorption spectrum that you necessarily expected. So there must be a broad continuum source with consistent and stable radiant power across the full range. So as you can see here, I mean, it's still okay. It's only like an order of magnitude. There are some which are worse, and so they're not used. But a deuterium hydrogen lamp produces continuum UV light in the same process. So even though this is deuterium and hydrogen proceed in the same way. So deuterium plus some electronic energy will produce an excited deuterium And then this excited deuterium molecule will decompose into two different deuterium atoms. And then the splitting of this bond, the D bond, will emit some light, this HV. So this will be energy that's emitted as light, and this will be the production of this light here. D2 lamps are preferred because the output is larger and brighter than H2. Yeah. But you could use hydrogen, I guess, in a pinch if you really wanted to. If you needed like some lower energy application, like there are some like applications that you can't use very intense light, like perovskites, the sort of the modern researched material for solar cells, perovskites. They often are not suitable for measurement using very, very bright, intense sources of light that tends to just destroy them. So components here, so we have sources, the visible sources, so tungsten filament lamps. So we have black body radiator, we have a range of between 350 and 250 nanometers. We have a glass envelope, and we have 2,870 Kelvin filament operating temperature. So these tungsten halogen lamps, excuse me. So as we said a moment ago, these tungsten halogen lamps contain iodine inside of the quartz envelope. So they have a very high operating temperature, which can go up to 3,500 kelvins. This is higher than the original tungsten filament lamps, which are much lower temperature. And then the presence of this iodine within the quartz envelope. The quartz envelope is the glass which surrounds the filament. This increases the lamp lifetime due to the formation of tungsten iodide, which is redeposited on the tungsten filament. So basically what happens is that the tungsten, through the process of generating the light, will kind of be evaporated by the high temperature. But then whenever it's evaporated, it's contained within this quartz envelope. So it goes out into, it's sort of evaporated as a gas inside here. Then it comes into contact with some iodine, and it reacts with the iodine due to the elevated temperatures to form tungsten iodide. And then this tungsten iodide condenses onto the tungsten filament, at which point the iodine is evaporated off, and the iodine goes back into the gaseous form inside of the envelope. So other types of light sources, such less common, are like LEDs. We can have semi-monochromatic. So these are semi-monochromatic and are more environmentally friendly because they generally need less electricity or energy to produce the light that they do. They don't have these very high operating temperatures, such as the tungsten filament lamps. But they can be more expensive. Sometimes they're not always available in the wavelengths that we want. And then the other one are the xenon arc lamps. So these are the ones that I talked about with like the perfect range over the full UV to visible. The problem being that they're kind of expensive. Then this is like the monochromatic source of radiation from a particular LED. You can see it goes from just below 500 all the way up through the near IR here at these wavelengths. The problem with this is, though, that this particular LED does not cover the UV or even the full visible range. It's also got very low intensity in those ranges. So it may not be suitable for a UV vis type measurement. Line sources then, so we talked a little bit about line sources earlier in the sense that they produce very discrete wavelengths. Typically, these are used in things like what do you call this? Used in atomic absorption spectroscopy, because we can often, the way that works, and we'll see that later, involves having lamps which are tuned specifically to a few elements. And so they're very good at that. So these line sources produce few discrete wavelengths, deuterium lamp or mercury xenon arc lamp for wavelengths below 400 nanometers. We have atomic emission hollow cathode lamps. So this is the one that you would use in an atomic absorption or atomic emission spectrometer. We have electron bombardment of the cathode, we have sputtering of cathode atoms, and then the emission from electronically excited cathode atoms. So that's the process of this hollow cathode lamp. So what happens is that the cathode, which is made of some metal, is bombarded with electrons from an electricity source. The sputtering of the cathode atoms then proceeds, and then emission from the electronically excited cathode atoms, which have been sputtered, occurs. So this is what it looks like. So we have some electricity source, which will bombard the hollowed cathode with electrons, which will sputter some atoms out. And then those atoms will release light as they are ejected. And this will cause a beam of light to pass out through this lamp towards our sample or into the optical circuit, which can be pointed towards our sample. So the hollowed cathode lamp is made of the analyte element. So we have to have a specific lamp for each element. So if we wanted to measure iron in our sample, we would need a lamp which had a hollow cathode made of iron. If we wanted to measure, copper, we would need to have a hollow cathode made from copper. Whenever we're using these hollow cathode lamps, they are very specific to the analyte element. They do not measure molecules, they measure only elements, so atoms or elements. We have then the tungsten anode here, that's just to balance out the circuit. Then the hollow cylindrical cathode is made of the analyte element, so that's the copper or the iron or chromium or whatever it happens to be. Then we have this bulb, this light glass tube filled with neon or argon, which is a non-reactive gas. And then, yeah, it says here, as I've said, we have a specific lamp for a specific element. You cannot use, for example, a lamp for sodium to measure iron. And the reason for this is going back to our electronically excited states that we talked about before. So each element has a certain energy difference between its ground state and its first excited state, for example. So since those produce a unique fingerprint for each element, the energy transitions. What that means is that each one of those transitions from 0 to 1, say in iron, is 200 nanometers. It may not be 200 nanometers, just for the sake of argument. That means that whenever we excite that iron, here we're producing excited state iron atoms. Now, whenever they are on the first excited state, they want to go back to the ground state. So whenever they relax from the first excited state back to the ground state, what happens is they release light. But that light has a wavelength which is exactly the distance between those, which may be 200 nanometers in the example that I'm giving. That means that that 200 nanometer light can actually be used to excite other iron atoms, and only iron atoms, because they're the only one in this example that has a 200 nanometer gap between their ground state and their first excited state. Other atoms may have energy differences which are much larger, like they could be 250 nanometers or something, or just significantly different, which means that the 200 nanometer light would not have sufficient energy to actually excite that particular element, and therefore it could not be used for that element. So for the hollow cathode lamp, monochromators cannot isolate lines narrower than 10 to the 2 or 10 to the minus 3 nanometers. So that's 0.01 and 0.001 nanometers. So these are very, very narrow lights. So we need to get narrow lines of the correct frequency for the hollow cathode lamp. So this is why the hollow cathode lamp is necessary, because it can produce these incredibly accurate lines, these like the lines with exact wavelengths. A monochromator is, as we'll see later, a way of separating monochromatic light. So monochromatic light, which has a broad range of frequencies, it can be separated using a monochromator. But there is a limit to how separate the lines can be using monochromators. Monochromators, even from the name, you can kind of get it. Mono means one, chromator means light, or chrome means light, so it makes one wavelength of light, basically. So we use a hollow cathode lamp containing analyte element to get those narrow lines of the correct frequency. So a high voltage is applied between the anode and cathode. So there's the anode, here's the cathode. Filler gas is ionized and positive ions are accelerated towards the cathode. So the anode produces positively charged gas, neon, or argon, and then this is accelerated towards the cathode. Then the sputtered positive ions strike the cathode with high energy and sputter metal atoms from the cathode into the gas phase. So the sputtering is a process by which you're basically hitting something and then bits of it are shattering off, sputtering off. The free atoms are excited by collisions with high energy electrons, and that causes photoemission. So basically, in almost all of these processes, what is happening is there's some energy source. That energy source is sufficient to excite a particular source of light, whether it be a tungsten filament, whether it be the hollow cathode here, whatever it happens to be. The energy that we supply, usually from electricity, will be sufficient to create that transition from the ground state to the excited state. And then as it relaxes back down again, it releases some energy, and that released energy is the light that we use. So the atomic radiation here is the same frequency as that absorbed by the analyte atoms. That's because we use, for the hollow cathode lamp, we are utilizing a specific hollow cathode lamp for each specific element. So iron hollow cathode lamp is used for iron analysis, copper for copper, sodium for sodium, and so on. So the cathode shape is cylindrical, focusing the emission in a beam, which passes out through the quartz or Pyrex window, and each atom absorbs at different wavelengths. So to analyze the element, light from the element is needed. Just reiterating the same process. Electrodeless discharge lamps. So here we have a similar, well, a different process, but we can produce light of specific wavelengths based on the RF energy that we use. So inside of this sort of lamp, which I guess is less utilized in most instruments, at least the ones that we come across regularly, because of their cost usually. This radio frequency coil here is wrapped around a lamp. This coil then can produce argon ions, because this whole thing's filled with argon gas, produces argon ions, and then they collide with the gaseous metal ions, and then they emit a light based on the excited state relaxation. Okay, so lasers then, these are the other major light source that we'll discuss, probably the last major light source that we'll discuss. Lasers have, we'll discuss it a little bit today, and then we'll go over it again next time. Laser stands for light amplification by stimulated emission of radiation. It is an well, initialism, acronym. Anyway, it stands for something. You don't really need to know that. You just need to know it's a laser. But it has two main processes. There is the pumping of an excited state, and then there is a stimulated emission to produce emission. So what does that mean? So we have to fill up a certain excited state in the molecule or compound with excited state electrons, And then those are going to be used to produce our laser light, but in a very specific way, which is one of the real benefits of using laser light. And it's utilized in a great many applications. But it's important to understand how the process works. So what is this idea of pumping? Well, this idea of pumping is literally trying to get as much of the ground state into the excited state as possible. So pumping is the process by which active species of a laser is excited by means of an electrical discharge, passage of an electrical current, or exposure to an intense radiant source. So many lasers are actually pumped using another laser of higher energy, which is usually a continuum laser if we want to get like a pulsed laser beam. So some electrons are excited to higher vibrational states, which have a short lifetime of 10 to the minus 13 to 10 to the minus 15 seconds. So these are the excited states. They relax very quickly. The electron relaxes to the lowest excited vibrational level, EY, and an undetectable quantity of heat is produced. So we have here EY. So this is the excited state, the EY excited states. So this is the lowest energy vibrational state of that first excited state. We have different vibrational states. We've got E triple prime, E double prime, EY single prime. Now, whenever we excite and we pump this, we're doing it rather indiscriminately. So what's happening is we're pumping it from the ground state up to the various excited states which exist here and here. Then it undergoes partial relaxation as they go from, for example, EY triple prime down to EY, which is the lowest vibrational level. And so that process takes a very short period of time, 10 to the minus 13, 10 to the minus 15 seconds, and a very, very, very small amount of heat is produced. This is why these lasers typically need to be cooled in some way, because even though a very small amount of heat is produced, since there are so many different atoms within, or since there's so many atoms within the compound, the energy or the heat that is produced actually is quite large. So after we excite, after we pump, pumping is just another word for excitation or mass excitation. There is some partial relaxation, and then we have a metastable excited state where for a short period of time, this excited state, EY, has all of the electrons in the same energy level. This is before they would relax down to the ground state. They're in this what's called metastable excited state. So far, it's effectively the same process as all the other processes we've talked about with regards to electromagnetic radiation. We start off with a ground state population, then we excite it to the excited state, and then after that, they relax down to the lowest vibrational level of that excited state, and then we have what's called a metastable excited state. Then after that, basically the electron relaxes down to the ground state, and then that relaxation emits light, and so we have light. That's so far it's exactly the same process as for our tungsten filaments, and then that happens very easily. So then we have relaxation, so we produce one photon of light from one relaxation process, then the other one relaxes, we create the second photon of light. Wavelength of this light depends on the energy differences between this and this. So the wavelength is equal to hc. H is the Planck's constant. C is the speed of light, all over EY minus EX. Well, speed of light in a vacuum is C. Then we end up with the electrons in their ground state. And so we have two emitted photons from two electrons, which were in the metastable excited state. So this is the same process as fluorescence. An excited state species may lose all or some of its excess energy through spontaneous emission of radiation. Now, the problem here is that this is why the laser had to be produced, was that the spontaneous emission is uncontrollable. It happens when it happens, and it's kind of hard to control the amount of light which is produced. So especially if we want it to be in a very specific energy or in a very specific manner. So after that, we'll move on to ways in which we can produce more consistent amounts of energy, and then see how lasers actually function inside of devices. But that'll do us for today. I don't want to go into lasers in too much detail. I just wanted to introduce them. The process is largely the same. It's about exciting electrons. It's about electrons relaxing. And whenever the electrons relax, they generate light. And the light has a wavelength which is specific to this energy level difference. And this is the same reason why we have to have this. Oh, okay. Going off topic, this is the same thing that happens in hollow cathode lamps, and it's the same reason why they have to be like they have to have a specific element for each one. It's because the difference in these energy levels is different for each element, and so the wavelength of light that is produced is going to be different for each element. Okay, so that's us for today.